Go ahead.
Good morning. Today is May 4th, 2022, and we are under the auspices of Ontology Summit 2022. We are in the session for synthesis of the third track, which is environment disasters. I have 50 years part-time exposure to Earth observation satellites and data and images. I thought I would present you a summary of whatever I could find in terms of current status, as well as the technology behind the disaster data that we use. Most of us who are new to this application space do not necessarily know what goes behind the acquisition of data. So I thought I would spend 20 minutes or so discussing this canvas. So I will go into platforms which can be on ground and ocean buoys, can be aerial, or can be satellites as usually are. And the satellites are of two types. One is low Earth orbit and the other is geostationary. Geostationary is having obviously lower resolution and is used for mostly meteorology, weather forecast, or other dynamic coarse resolution phenomena. While the low Earth orbits are capable of getting to meter or sub-meter kind of spatial resolution. And temporal resolution depends on number of satellites, because at each local time, usually these LEOs travel at a given time, AM or PM, usually around say 10 AM local time. So if you want continuous coverage without gaps, you need more than one of these. We'll see them later. What goes into these satellites are sensors, and typically the 3 or 4 kinds that come to mind are multispectral sensors. And since we can see things through windows in the atmosphere where the sunlight is falling, so we range it from 3 to about 100 micrometers for visible infrared, and more than 30 bands on each scanner or sensor, up to 30 bands. The radiometers, they integrate and collect radiation. There's no active item like sun, so we can use it for naturally emitted radiation like microwave radiation from the Earth or in the IR or microwave region. Then there are active sensors like radars and laser radars, so laser reflectors. They bounce off the surface. They go up to some depths, depending on the wavelengths and the intensity. And these are illustrated here. For example, when sun falls and you get reflected light, transmitted light, or scattered light, that's one kind of sensors. And the active is where you carry the source in the satellite and bounce it off the surface or ocean or snowpack. In all of these, the importance is of the electromagnetic spectrum. And the reflected spectrum contains some information on the phenomena that we are after. So, as we will see, water, vegetation, and land give us different kind of reflected or scattered signature. The nature of the signature is also important. If we are looking like a mirror with a very sharp focused light, we get specular reflection. If you get a white bulb in which you can't see the filament like a tube light, it's called diffuse or Lambertian reflection. When molecules scatter, you get Rayleigh scattering. And when you have particulate matter starting from submicron to a few micron size, as in clouds, as in pollution, aerosols, measurements of all types, then you have me-scattering, where the interesting phenomena take place when the size of the particle and the wavelength of light are comparable. Interesting. Otherwise, me-scattering has, like really, a good cross-section. So this required a lot of knowledge. Some of it was coming from astronomers who were looking at IR, looking at deep space, and some of it came from earth science disciplines such as USGS. I am confining mostly my experience to US and NASA, and some experience from India, the Indian space program. And I have familiarity with some of the ESA programs as well. Of course, I don't have as much familiarity with the China emerging program, but I can say that in 2000, I was instrumental in teaching a group of, or training a group of a dozen young Chinese scientists who came under a contract to use Raytheon towards the end of last century. And within few months, they picked up a lot. And you now see that they have probably half a dozen or more Earth-looking satellites. Here we are looking at the solar spectrum, and you see a little bit of attenuation because of intervening all kinds of space, some ionosphere, some atmosphere, and so on. It says 6,000 degree Kelvin black body radiation. So when we go to higher wavelengths, beyond visible, which is visible is like 0.7, 0.8, 0.9 at the most. At 0.9, we call it reflective IR. And right around here, as you would see, the vegetation, which is dotted line, reflects differently, and concrete and soil in one way, and water absorbs in this wavelength. So we can distinguish chlorophyll, water, and landform very nicely. Here is a black body radiation in thermal infrared, and I would request you to concentrate on this 2 to 20 micron range here. It's a convoluted logarithmic scale, so it's hard to imagine, but a 300 Kelvin black body is also depicted here. And you see a few peaks that are of interest of absorption or reflection: water, oxygen, or ozone, and carbon dioxide. So different species have their signatures, just as in any spectral signature work you might have done. Fraunhofer lines in the sun, Raman spectra, all other kinds of electronic transitions in the outer shell of the atom. So what are the factors that are important? Goniometry is the most important. Incidence angle of your radiation and the imagine a full circle or a cone of 180 degrees for observation. Imagine a specular light like a sunspot on water and imagine looking at it from all different sides in a cone. That's called goniometry. Spectral irradiance, obviously, we have discussed passive and active. Now, the data sources are important, we'll come to them, but supplementing or verifying is done by ground truth, which is listed here. Then we collect all these data continuously from orbiting satellites, and we create metadata so that our search and retrieval becomes possible in as technical a manner as possible, as the data would allow. So, and the products are generated. Sometimes they are image data products, and sometimes they are just electronic data records, like as tables and so on and so forth. Are you able to hear me clearly?
Yes, we can hear you.
Yeah. Thank you. This is just a recent copy from NASA webpage, but just looking at the pattern, we can see the evolution of Earth observation and related ocean atmospheric satellites. Quite a constellation. And when we come to our space debris fourth track, we will have Robert Rovito, our colleague, speak to us on a full session about how they are crowding the space around us, near Earth space especially. But the three satellites that I had to deal with in planning, but remember now, we are in Landsat 9, and Landsat 1 and 2 were called ERTS, Earth Resources Technology Satellites. And there I was involved a little bit in terms of selecting the 4 spectral bands that went in 1972 in our NASA's first Earth Resources Technology satellites, 2 of them. In the second one, we added a thermal IR and band. So the atmospheric attenuation in these bands, how much it would be, and what kind of opacity it would give us in the image, and how do we correct for that, as varying the different atmospheric parameters enter when you take a picture over a large area. That was all one of my areas of expertise with Bob Turner at University of Michigan, using Chandrasekhar's radiative transfers as a theory. Most of it I've probably forgotten by now, 50 years later. So the first satellite we saw, which looks at land, it is some kind of radiation and landforms and carbon monoxide, is Terra, the Earth-looking satellite. There are 3, Terra, Aqua, and Aura. More or less, they're all functioning still, but the latest, if you want latest data, it is Landsat 9 and subsequent plant satellites. So most of them have this kind of orbit, 700 kilometers, and they have some fixed node local time. Here it's a PM, so it's 1:30 p.m. AM is where I said around 10:30 in the morning. This is just last week, April 29. recent imagery incorporating a storm, atmospheric storm in the desert area, Sahara area. And these are some of the lists of the sensors involved. The aura sensors for atmospheric chemistry. Some sample we are giving here. We are also now introducing you on this slide to a standard, which is called hierarchical data format. It's a self-defining standard, whereby by reading, as we used to do in tapes, if you remember, or discs, the first track would define what you expect. And that would be a formatted, well-known sequence of data with which you would unravel what is on the tape. Similarly, this multi-parameter swath, time, width, resolution, other kinds of parameters were standardized right when I was with NASA around the 96 to 2000 time frame. This standard evolved, and University of Illinois Urbana-Champaign, Mike Folk and others consulted with NASA to evolve these standards. Now I have 4 here highlighted sensors that go on this aura. So remember HMOT, we'll need to remember that later. So these are some facts for the aura satellite, similarly to others. However, now we are beginning to learn by creating image data products at different levels, the synergy, and as my friend Gary Bird-Cross would like to call it, a lot of harmonization among data gathered by different platforms. So here we have Aura, we have Parasol, some European satellites, Aqua, and so on. And of course, there are GOES, which are in different orbit, and some are even in geostationary orbit. We do formation flight and constellations of satellites, and then align the images to reach goniometric parameters and change parameters. This is slightly illustrated here. If we were doing aerosol studies, the aerosol is non-uniform object. So depending on the incidence and the observed angle around the orbit at different times, we would see different aspects of the scattered or reflected light. And so we can determine how much energy is absorbed, the shape of the particles, and probably we can trace the lineage, where they came from. Are these extraterrestrial, volcanic? Are these meteoritic? Are these snowfall, aerosols, etc.? I have worked a lot in aerosols, but mostly from the point of view of contamination of the spacecraft, because everything we observed during Apollo and Skylab was through a cloud that surrounded, however thin it might be, with particles and gases surrounding the spacecraft while we were observing the sun, the moon, and various things in between, including dumps of oxygen, hydrogen. And here is a 1964 to 2012 greening of the Arctic. Some 87,000 image composition has been composed to show that progressively we have greening of the Arctic, and implying that obviously there is warming of the Arctic. Here is an image of the Landsat 9. I'm going to show 3 different resolutions. This is just 2 days old, 2nd May. Obviously, you're looking at India and the Himalayas here and some cloud forms. And the resolution is 1,000 kilometers, and it's multiple bands in these so-called layers here up in the lower upper left corner. Can you see my cursor, or probably not? So here is the next resolution, which is 200. From 1,000 we came to 200. Remember these clouds here? We are seeing them in this expanded or more resolution, higher resolution. Here's a still higher resolution. And by the way, I like this picture because it shows my hometown around here. And this little white speck is a salt lake from where a lot of salt comes for supply to India. So, and obviously, I come from a city of about 6 million people. It's a small city in India, but it's a state capital. Here is some dated material. I looked at the same area about in 2007 when I gave a talk at University of Delaware on remote sensing. And remember, these were the kinds of satellites data available. So we have a lineage of about 20 plus years. For each of the sensors, like what you saw here is MODIS. MODIS is that, remember, its various avatars or versions have gone from originally 13, 14 spectral bands to about 30 now. Wears and MODIS are still keeping their name, and they have that kind of, and this is just a sample list. It goes down. I didn't go all the way. For each of these sensors, we need to create a document that talks about calibration, kind of theory, kind of geometry, kind of math or physics you have used, so that people can correct for various things and parameters as they refine their image. Here, we are talking of how we get all that data. These are all satellites giving down the data. They come on a downlink. They get acquired across the globe wherever the satellite is visible to the ground station. It's a fairly large cone of reception. So from nadir to horizon, back to horizon, horizon to horizon through nadir, you are able to get a lot of data acquired by stations like these. Then they come into processing area. In the operations centers, there are central still, unless it's weather data where they are directly distributed to fishing people, to the weather affected forecasting people, and so on. They go direct unrefined data, but for most other Earth observations, they get processed in the data active archive centers. Will come to them, and these are the kinds of things. And ESIP is one of these activities, and my colleague Gary Burke-Cross is involved in ESIP, Earth Sciences Information Collaboration Partnership. How many data active archive centers? They are data active archives because you can retrieve old data as well as real streaming data are coming to these locations. And the two that I am most familiar with are one as Goddard Space Flight Center, where I worked both on the scientific data archives, including GPS, geodesy, ionospheric, etc., but mostly the SDIS, for which you had a distinguished set of speakers, Karen Moe and her colleague Dave Jones in the Storm Center now, but Karen was the program manager for this SDIS all Earth Science Data and Information System, DAC. The physical oceanography, like planetary archives, is located at JPL. And there also I have spent some time, a few months, while a few years at Carter. And of course, at headquarters during Apollo and Skylab. So these are the active facilities. We just talked to you about HDF. Here is a little more detail, self-describing. I hope you can read some of it. They are much more compact than ASCII files. And they carry a lot of metadata. And we'll see some of them out here. As probably this says that Esri and MATLAB and Mathematica and MATLAB are able to read HDF format files. These are some of the metadata I would like to call in the first column. And these are some units and so on. And the measurement units, I mean the formats. And these were the 4 sensors, remember, on the aura, which is applicable for which of these parameters or metadata. So this gives you an idea of how rich the metadata definitions are in the HDF EOS format. We have graduated from storage stack silos, online disk drives, to now clouds, which are in the big, huge silos of disk arrays underground, and wherever the cloud data is stored into petabyte architectures in each of these dozen or so data active archive centers. The data are processed at different levels. Most of data is kept along with calibration of sensor, orbit, time, and other stamps at level 0 and is distributed unprocessed for most applications. But where there are corrections required, for example, you want the image to be geometrically correct, so you can overlay it in time, or you can co-locate the edge of a mountain or the course of a river or something, which is a ground control point, then you would want level 1. And then if you want the measurement of the reflectance, scattering, or other intensities, then you want level 1 radiometrically corrected. Like this, different protocols are used, and these are the 4 levels, L0 to L4, 5 levels of data available in the archives. This is again another description, little verbose, of what these levels mean. So obviously at higher levels like 2, 3, and 4, supplemental data like from USGS, topo maps, and so on are used to define contours and boundaries. And by the way, for contouring one shuttle, a very good active sensor is still being used all over the world from space shuttle active radar data, which gave a lot of topography of the globe. Now we talk a little bit of the kinds of disciplines we are interested in. This slide, I think I probably showed in the beginning of our summit. I'm not sure if I have. But this just says that there are these 2 broad areas, and we still have challenges. Some parts where remote sensing can help, some where it can't. For example, nuclear waste management is a big Earth problem. If I could make the launch of rockets into sun reliable and inexpensive, I would get rid of all the nuclear waste and throw it back into sun where this process anyway naturally exists. So, but that is some ways away. It's a fiction right now. These are again disciplinary areas and some links from NASA. Probably Gary knows more about LANS, which is land atmosphere near real-time capability for EOS. That's where ESIP and others are also active. Just saying that it's not all for posterior analysis. Some of it is available as we get the data from satellites and is useful for real-time, near real-time problems such as fires. These are some of the links, some are still active, which take you to various sensors and their data and downloads. We are going from UV to radar, entire range of electromagnetic spectrum. These are satellites, these are the sensors, and there's a little description. So remember the formation flights? Two things, harmonized Landsat and Sentinel was European satellite. Together, how do we harmonize? There's some blurb about that. And there is a very interesting phenomena, especially in vegetation and forests. It's BRDF, bidirectional reflectance distribution function. And that is, these two help in the goniometry analysis, angles, reflectances, ability to discern different types of vegetation or different structures of grass, let's say, tall, small, smooth, rough, etc. in surface properties as well. So this is that harmonization effort depicted here in terms of these kinds of products. And we are beginning to use the capability of multiple satellites. Finally, coming towards the end is the metadata slide. This is what relates closest to our topic of ontologies. I won't dwell too long, but we all know, we have seen a lot of them up there in different slides. These would make sources. These are the sources from which we have to do a lot of massaging or juxtaposition or overlays and extractions to derive an ontology, a dynamic ontology. Static will not work because things do change. Metadata attributes are changing. So we would have to use these to extract ontologies, which is the topic of our summit. Some has been done, some samples you have seen from some of our speakers, but this is what goes behind the scene before you can derive these ontologies. This is self-praise. Obviously, the ego is the last thing to go from one's life. So ego stays till the end. And this is the advertisement of my ego of last 50 years, what I have done in these areas, starting with Landsat and Apollo. Apollo was the first. Skylab was next. Landsat was next. And then space shuttle sortie missions, where I was the principal investigator for Earth viewing. Then I went to India and started the first remote sensing satellite there. It was a tough negotiation with the Soviets at that time, but I got the Bhaskara satellite, which was first visible and microwave sensor satellites assembled by India, launched by Russia at that time, Soviet Union at that time. And then I came back and I worked at Terra, Aqua, Aura, and POS, and other data archives. So life has been very good, very rich in being able to be an imaginary object in space, looking down at this beautiful earth and also looking at not so beautiful contributions we are making to the pollution and the environment. And some disasters are natural and we have to manage them, but the other disasters are human caused, lack of education, lack of resources, many reasons. We can open that to debate, but my talk is over and I think I took a little more than I wanted, maybe 10 minutes more. But we have another presentation for synthesis session. And unless you have questions on this, with Ken and Gary's permission, we can move on to the synthesis session slides. I'll wait for some questions.
Oh, I have a bit of a question. I mean, you have lots of observation satellites. To what extent are they real time versus just, data that's captured and then, provided in file format?
The downlink data is available to anybody who can create an Earth station of their own. For example, for ERTS 1 and 2, I set up a large, I forget how many feet, probably 60-foot diameter dish with tracking capability to receive Landsat data. So any part of the globe, just like we are now receiving TV programs through cable, direct dish, we used to receive Earth science data in real time.
So that's real time.
However, processing in real time has been a challenge, and the biggest beneficiary obviously are the NOAA and atmospheric users, because atmospheric phenomena require you to understand and grasp the severity, onslaught, and likely impact on you. So those were given even to boats, small terminals, on boats, on the land, at each weather station, at each TV station, to receive quickly in real time and give data, but mostly atmospheric data, little bit oceanic data. But for real time, for example, wheat takes so many days to grow, so there are only so many passes, and you can synthesize wheat growth slowly through classification algorithms and machine learning. And two different schools of thoughts, one originated in Michigan, another originated at Purdue. Purdue believed in clusters like the Soviets did, and hydrometeorological services of USSR always believed in landform cluster classification, as did Purdue. And Michigan believed in training set approach of machine learning. So we knew that this was wheat, this was water, that was forest, a priori. While in clustering algorithms, we don't know. And Bayes' theorems are used in both.
Yeah, so you can get it in real time. Now,
Yes.
I was thinking more in terms of using things like change point detection algorithms. So detecting phenomena that are occurring in real time.
Yes, some of it at level 0 is certainly available, but you require a facility.